Hi everyone, welcome to Mostly Math. Today we are going to investigate the Airy function, which satisfies the differential equation d squared y by dx squared minus xy is equal to 0. This is a second order equation. It's not separable. It requires special methods to solve it. And in this case we are going to use the Fourier transform. So let's go ahead. Start by writing 0 equal to d squared ai by dx squared. So ai of x satisfies this differential equation here, minus xai. And now to solve this in the Fourier transform space, formally we would transform both sides and use the properties of the Fourier transform. So in K space, we make the associations of x goes to I d by dk and d by dx goes to ik. And continuing on, second derivative, so we're going to have ik squared times ai, now as a function of k, minus x, which is just I d by dk, and multiplying by I to clean it up a bit, we're going to have a minus, first term here becomes I squared is obviously minus 1, so that becomes minus I. And second term is going to be minus I squared equals plus 1, of course. So it's going to be dai by dk minus I k squared ai being equal to 0. So notice this was our original equation here. Second x derivative minus x times ai in the x space being equal to 0. Our new version is the first k derivative minus ik squared ai being equal to 0 in the k space, which is actually much easier to solve, which we will do now. Since we have a first order homogeneous equation, it is now separable. So we can write integral of dai by ai is equal to I integral with respect to k of k squared, which can be very easily evaluated as log of ai on the left and I over 3k cubed on the right. Exponentiating both sides, we have ai as a function of k is now e to the I over 3k cubed. So that seems easy, but it's not really what we wanted. We have ai of this k variable, which is really different from the x variable. And in fact, what we have here is the Fourier transform of ai of x. We really want ai of x. So let's just take the inverse transform. This is actually why we wanted to use the Fourier transform in the first place, so we could reduce the order of the differential equation and make it separable, solve it in the Fourier space, inverse transform back. That's the reason why we would want to use a transform method on a differential equation in the first place. My favorite definition of the Fourier transform, there are many, goes like this. If we had a function in x space and we wanted it in k space, we would simply integrate over all space, multiply by x, e to the minus ikx, and the original function of x. This is the Fourier transform. And if we wanted the inverse transform, this would be we had an f of k, and we wanted to get an f of x, we have to multiply by 1 over 2 pi by convention. We would integrate with respect to k, e to the positive ikx, f of k. Just standard definition. So this is the Fourier transform, this is the inverse Fourier transform. And let's apply the inverse Fourier transform to our expression here. Pretty straightforward. So we have ai of k, ai of x is just then 1 over 2 pi to go from minus infinity to infinity with respect to k, e to the I kx, e to the I over 3 k cubed, which we can obviously combine as e to the I kx plus 1/3 k cubed. And we'll want to use Euler's formula next. Eventually, we want to get a real answer for our function. Since it's a real differential equation, it should have a real solution. Euler's formula is a good guess about how to proceed in getting that. So we're going to have 1 over 2 pi. And the first integral is going to be cosine of this stuff. And the second integral is just going to be I times sine of this stuff. And we are fortunate, in this case, this integral is actually 0 since it's the integral of an odd function over a symmetric domain. This is a powerful theorem. Basically, if you have something like x and this area, is equal to that area, so they're going to cancel out. All right, and the cosine integral is obviously even. It's equal to twice the integral from 0 to infinity, and that's our final answer. So our ai of x is just 1 over pi, integral from 0 to infinity with respect to k, cosine of kx plus 1/3 k cubed. That's our final answer for ai of x. It wasn't actually that hard to get the inverse Fourier transform, so I think it was justified in transforming the equation to get the solution. It's going to, this form I've written here trivially is going to be different from the Wikipedia article since they use the variable t instead of k. But I think it's illustrative to use k because it shows you where this comes from the inverse Fourier transform. Okay, so if you want, you can stop the video here. But I think it's cool to actually plug this function into the original equation and show that in some way it satisfies it, since this is a pretty weird function, especially the 1/3 k cubed, which is the interesting bit. So let's go ahead and write the original equation down and check and see if it satisfies it in some way. Just to satisfy our curiosity. Not strictly necessary, but let's do it anyways. All right. So, our original equation for ai that I was supposed to satisfy was d squared ai by dx squared minus x ai is equal to 0. So let's just go ahead and take some derivatives, multiply by x, and see that it satisfies this. So first derivative, respect to x, we're going to assume that we can take the derivative inside the integral sign. We're going to assume that all of the conditions are met for these functions since we are a physicist in this video. And when we do that, we have to take the cosine to minus sign and bring out a factor of k since we're differentiating with respect to x. dk k sine. Also, notice we cannot bring k outside the integral since we are integrating over a k. This is a mistake that I made early on. And the second derivative, well, we have a sine, it's going to go to a cosine, and we're just going to get another factor of k. Minus stays there as well. K squared cosine kx plus 1 1/3 k cubed. Awesome. So now we just need to take this and subtract from it x minus this, basically, since we have the original function with the k here. When we do that, we have the left-hand side of our expression up there. This part is just going to be minus 1/pi integral from 0 to infinity with respect to k of, let's see, we're going to have x plus k squared cosine of kx plus 1/3 k cubed. And it should be immediately obvious upon looking at this integral that somehow, miraculously, it's already in the form of integral of cosine u du, which we can readily evaluate. This is just, need to erase our AI now. Minus 1/pi to go from 0 to infinity with respect to a new variable, kx plus 1/3 k cubed, times cosine of this variable, which just evaluates to sine of this variable, evaluated at the endpoints. So the 0 endpoint is not going to cause us any difficulty. It's 0. The infinity one, and the mathematicians are not going to like this, 1/pi, minus 1/pi sine of infinity, which as a physicist we are going to say is 0, which we know it's not, but because it oscillates between -1 and 1, its average value is 0. Historically, many pre-Cauchy mathematicians and pre-Weierstrass, basically the pre-analysis mathematicians would say it's 0 as well, because it's necessary in our instance to satisfy the equation. But if you want to make it more rigorous, you can turn this into a principal value integral using complex analysis. I'm not going to do that. This is good enough for me. I think it satisfies it to the standards that I'm holding myself to. And I just wanted to learn more about the Airy function. Since it is a pretty rare special function, you can find it in tables and so forth, but actual derivations of this sort are harder to come by. I hope you enjoyed this elementary introduction to the Airy function, and subscribe. See you next time.